number 4, we will finish the pipe flow section. Okay. Now, the topic number 4 is talking about the analysis of the pipe network. Okay. Now, what kinds of the networks, pipe network we have usually? In most of the time, we will have these 3 types of the pipe network. This is the pipes in series. Okay, pipes in series. Pipes in parallel and branching pipe. For the simple pipe network, we mainly talk about these 3 types. Pipes in series, just the pipe linking one to another, okay, head to tail, linked together in a straight one flow, okay. Pipes in parallel, mainly talking about this the junction linking 2 junctions by 2 or more pipes, okay. This is the pipe in parallel system. Another one is the third one is the pipe branching pipes. It is usually talking about the numbers of the pipes that link together in one branch, but in different outlet or inlet. Okay, these are 3 main simple pipe network. Okay, simple pipe network. We will talk about one by one. How to solve? What kinds of the information usually we will focus for this system? 通常我哋去睇呢個嘅 pipe system 嘅時候，我哋最主要係 focus on 邊一啲嘅參數嘅？大家會諗下。我哋通常會想最關注係啲乜嘢咧？高度知道。OK， 高度即係嗰個energy head 係咪 ？OK， 係啦，冇錯，呢個一方面啦。幾多個 in 幾多個 out？ 係啊，幾多 in 幾多 out？ 我諗你係想講個 flow 嘅，個 flow rate 幾多入嘅水同埋出嘅水。OK， 所以其實 so that we mainly focus on 2 things in this, no matter what kinds of the problem in the pipe system, in the pipe flow, we always focus on 2 things. One is the discharge, how the discharge is, and the head loss. Okay, how is the change of these 2 things, the discharge and the head loss? Most of the time we focus on these 2. Pipes in series, I think is very straightforward. Pipes in series. For the discharge, maybe directly right here. Okay. For the discharge, if there is pipe 1, pipe 2, and pipe 3, the discharge in a total, because it's one-way direction, according to the continuity equation, all the discharge in all the pipes supposed to be the same. Q1 is equal to Q2 equal to Q3. Right? All the discharge is supposed to be the same. Right? Now, secondly, for the head loss, along the flow direction, I believe that here the flow direction is going by this direction because the hydraulic brake line, the energy is going down, okay, along the flow direction. So the head loss along the pipes, total head loss is equal to the head loss in the pipe 1 plus head loss in the pipe 2 plus head loss in the pipe 3. Okay. This is the pipes in series. This is very straightforward, okay, understanding. So for the continuity, always consider the continuity equation and energy kinds of the consideration. Okay, the discharge must be the same because they are on the same line, and then the head loss is added together along the flow direction. All right, this is pipe in series. Next is the pies in parallel. Okay, pies in parallel. Pies in parallel. There will be two principles to follow as well. Okay, two principles to follow. The principle one, the pressure difference between the two junctions points is the same, must be the same. Okay, and then this is the first principle. Okay, the first principle. The second principle is that the continuity equation must be fulfilled. Okay. Must be fulfilled for the continuity equation. That means in this situation, so there are two pipes, there may be more pipes, okay? Now, for this two-pipe system, or maybe n number of the pipe, okay? There may be n number of the pipe N. For the head losses between the A and B, okay, A, B point, okay, the junction, head loss A to B is equal to the, we say that this is pi 1 and this is pi 2, and this is pi n. Is equal to the head loss in the pi 1 and equal to the head loss in pi 2 and equal to the head loss in pi n. Okay? Because the principle one, the pressure difference between the two junction points is the same. Because if there is difference in the calculation for the head loss between the two junctions, you have conflict, okay? One pipe the calculation is different from another pipe. There will be the conflict. So the pressure difference between the two junctions must be the same, right? So that no matter the head loss calculated in any one of the pipe connecting two points, there may be two pipes, 3 pipes, 4 pipes, or n numbers of the pipe connecting two junctions. All the head loss in the pipes are the same. Okay, in each pipes are the same. So this is the first principles to be followed. The second principle is that the continuity equation must be fulfilled. Okay, so the total discharge, it may be equal to the Q1 plus Q2 plus Qn. Okay, if there are n numbers of the pipe. That means because the main pipe, the total discharge will be branches into several pipes, maybe 2 pipes, 3 pipes, or 4 pipes, or n pipes. So the sum of all the discharge distributed in the pipe, the parallel pipes, must be summed to be the same as the main pipe. Okay, so that these two are the principles to be followed for the pipes in parallel. So sometimes that you may be asked to find out, okay, the distribution of the flow in the pipes. You will follow these two principles. Okay, maybe remember these two principles. Following later, we will talk about the pipe system. Okay, the complicated high levels. Okay, we will also use these two principles. So that's according to the head loss, the same principle. Okay, the principle one. For the head loss between the two junctions is the same. So we have the Darcy-Weisbach equation to calculate the corresponding head loss, and then so that you can estimate the velocity ratio is like this. Okay, it's just I think this is not quite important. Just show you that the velocity ratio distribution is something like this. But for the really calculation, we will mainly starting from this analysis. Okay. Next is the branching pipe flow. Okay, branching pipe flow. For the branching pipe flow, we mainly focus on the energy equation, following the energy equation, and also the continuity equation. Now, consider that the branching pipe system. Now, for the energy equation between this point and if there is times of manometer in the junction D, between the A and the junction D, okay. This is energy equation, okay. This is point A and point D. For the energy equation between the now, for example, between the reservoir A and junction. Okay. Now we mark the points that in the junction D, if there is a manometer here, okay, we put a point here. We may have the we see that this is point 1 and point 2, okay? P1 over gamma plus elevation 1 plus V1 squared over 2G. No pump and no turbine, okay? Only the head loss. Now, is equal to P2 over gamma plus Z2 plus V2 squared over 2G plus the head loss between the AD, okay, like this. Now, point 1 and point 2 are exposure to the atmospheric pressure, so they are all 0, okay? They are all 0. Now, velocity at the water surface are both 0, okay? So that the equation is Z1 is equal to the Z2 plus HLAD, okay? Now, Z1 is actually, here is the ZA here, okay? It's the ZA. Z2 is this one, okay? This is Z2. Z2 is here, okay? Z2 is composed by the these because point D's elevation is here, all right? So Z2 is contributed by the elevation of point D plus the because the piezometer installed here, okay? So we see that the pressure head at point D is PD over gamma. So it is ZD plus PD over gamma plus HLAD. HLAD is contributed by the pipes connecting the A reservoir and the D junction. Okay? So that this forms that the first equation here, okay? First equation between the A and the junction D. Now, we write this equation following the flow direction according to this system, okay? Now, because the A reservoir is flowing to D, D is flowing to branching into B to C, okay? Similarly, D to reservoir B, we can also write the, we may say this is point 2, and this is point 3, and this is point 4, okay? We have the P2 over gamma plus Z2 plus V2 squared over 2G equal to P3 over gamma plus C3 plus V3 squared over 2G plus HL D to B, okay? HLDB. Pressure 2, pressure 3, 0. V2, V3, 0, okay? Z2 is contributed by the PD over gamma plus ZD, right? Is equal to Z3 is directly the ZB plus HLDB, okay? And if we rearrange the equation solve for the ZB, it will be equal to the ZD plus PD over gamma subtract HLDB, okay? Similarly, from D to C point, okay, the ZZ is equal to ZD plus PD over gamma subtract HLDC, okay? So that's, we have these three equations. Usually, we are going to estimate, usually the ZA, ZD, B, C, and ZD are unknown. Okay? But three equations, four unknowns. Okay? Three equations, four unknowns. So we need to have one more equation to correlate these four parameters of these three equations. That, because this relationship we only based on the energy equation, we haven't used the continuity equation. So that we need to have another relationship, which is the continuity equation, focusing on the junction. Okay, focusing on the junction. We have in the junction here, the QAD is flowing into the junction. QBD, QDC, QDB, QDC is flowing out. Okay, so that the sum QE is supposed to be the sum Q out. Okay, according to the continuity equation. So that in the junction D, we have the QAD equal to the inflow, sum of the inflow supposed to be the sum of outflow. Sum of inflow to the junction D is QAD, okay? Sum of the outflow to the flowing out from the point D is the DB and the DC, QDB and QDC, okay? So in the previous three energy head equation, the head loss is represented by the Darcy-Weisbach equation correspondingly in each pipes, okay, AD pipe, DB pipe, and DC pipe, okay? And all of these pipes have the information, okay, velocity head, okay, oh sorry, the velocity is, the discharge is to be determined. Now, for the continuity equation, we have the velocity and the area for calculating the discharge in each pipe. In here, the velocity in each pipe are unknown. Okay, so that in this equations, finally, we'll have the info in four equations and four unknown. Okay, to the elevation of point D is unknown. The velocity in each pipe are unknowns. Okay, so we have four equations, four unknowns. So we may combine these four equations to determine the all the parameters. Okay, solve for the unknown variables. Now, to solve this equation, we can use the Gauss elimination, the linear algebra method to solve it. Okay, this maybe not. Okay, maybe unable to do so because there is power 2. It's not linear. Okay, so that things seems that we have to use the substitution method to solve it. Okay. Now, for the branching pi system, we may need to solve the equation system to find out the unknown parameters. So this is the branching pipes situation. We'll also have the tutorial question to show you how give you the example to solve it. Okay. Now next is pipes network system. Okay, pi network. Okay.